A very good evening to Dr. Noor Niza and also the external examiner. I would like to thank our supervisor who constantly guided us and helped us throughout this project. And I also would like to thank the UTP management and all those who put in their efforts to come up with this system despite our country's crisis. Moving on, the title that was given to us was Title 1, whereby Plant Design for Monetization of Plastic Waste for Chemicals Production. Now, moving on to the introduction of this project. Based on the background study, plastic was produced to reduce the burden of many parties. However, most plastics are not biodegradable. I understand the fact that many companies and industries produce biodegradable plastics, but in general, plastics are still considered to be non-biodegradable. And due to this, researches have been done whereby we can thermochemically convert this plastic waste into commercialized fuel. Based on our problem statement, the margin between waste plastic generated and the volume recycled is ever increasing. Development in the industry has caused various types of plastics to be produced, such as different chemical structure and also physical structure. Due to this, we cannot recycle all types of plastic. Thus, converting plastic into fuel seems like an appropriate solution to this crisis. And the objectives of this project is to design a process plant that is able to convert waste plastics to fuel as well as to achieve maximum conversion to produce high yield, and also to design a process plant with minimum energy consumption with efficient number of utilities with the application of heat integration, and lastly to accommodate the process plant with appropriate waste management facility by prioritizing environmental safety and health concerns.
I'm Akila. I'm going to present you literature review. So the raw material of our pyrolysis plant is waste polypropylene, and the main products are diesel, gasoline, heavy oil, and synthetic gas. So here is the 2D structure of polypropylene, and it is originally made from propene. And here are the physical properties and the chemical properties of polypropylene. Now let's move on to diesel and gasoline. So basically, the higher the percentage of paraffin, the better the quality of diesel and gasoline. For certain number, it is the measure of diesel ignition quality, which means higher certain number will lead to better performance of engine as it have more combustion, more complete combustion, and less emission in the atmosphere. Meanwhile, for the research octane number, which is RON, the higher the RON, the better in it to prevent knocking issue. Knocking is some sort of noise that coming from the engine due to irregular pressure. So some references here are expecting diesel to be increasing in demand, and some are expecting gasoline to be decreasing demand due to new technologies and the rises of electric car sales. So here, as you can see, for refer to the pink and yellow line, between year 2020 and year 2025, it is expected to be fluctuates bit for gasoline and diesel, and we can take our current situation as the example, which is due to outbreak of coronavirus. And China and India are the forecast top consumer of diesel and gasoline. Now let's move on to the third main product, which is heavy oil. So here are the chemical properties of heavy oil, and here is the physical properties. So it is expected for the heavy oil to slightly decrease in demand from year 2000, for the year 2008 until the year 2030 due to tightened rules of emission. So here are the average price trend of heavy oil. Since shipping industry comply with International Maritime Organization or IMO, the price of heavy oil become uncertain and cannot be forecast. So only average price can be referred, which is the blue line, from 1.5 to 1.7 approximately. And Asia Pacific, North America, China, and Europe is expected to be top consumers of heavy oil. So lastly, let's move on to synthetic gas. These are the composition or the chemical properties of synthetic gas, and physical properties of synthetic gas is vary on how it being created either by gasification or pyrolysis. So the forecast demand of synthetic gas is expected to be increasing due to the population growth of chemicals, fuels, and electricity sector. So same as heavy oil, these are the average price of synthetic gas, and the forecast top consumer of synthetic gas are China, Japan, and India. So, based on this market analysis, even though gasoline and heavy oil are showing slightly decrease in trend, in forecast trend, however, it still has demand and consumers, so it can be assumed as profitable products.
For the plant locations, I'll be explaining based on location options and also ranking factors. So there are three options that we chose for the locations of our industrial plant, which are Kerteh Terengganu, Shah Alam Selangor, and also Gebeng Pahang. So the factors that we will be assessing and comparing between these locations are listed in the most left column of this table. So the average pricing of land per feet is based on what we extracted from a website based on MIDA, which is Malaysian Investment Development Authority. TNB electricity tariffs was also extracted from the same website and is standardized for all three states. Energy availability, on the other hand, electricity will be outsourced as mentioned from TNB, but there are two utility facilities in Kerteh and also Gebeng called Centralized Utility Facility Kerteh and also Centralized Utility Facility Gebeng. These facilities supply certain number of utilities to the nearby industrial plants. These facilities are based on Petronas. The next few factors will be raw materials availability. So raw materials, we are assuming that we will be outsourcing it from solid waste management facilities based on each state. The next factor is markets, road transportation, water supply. So transportation is compared when we actually compare the distance between the location and also the nearest transportation hub. In terms of waste treatment, we have chosen Quality Alam as our option for waste treatment. Local community, on the other hand, is where we compare the number of community, the number of people in the nearby vicinity of the area, and also the distance of the nearby local residential area to the location of the plant. Climate, as you can see, is almost similar for all three locations. So these are the ranking guidelines. Based on the factors I explained earlier, we chose a certain number of factors so that we can rank based on the guidelines shown in this slide. So the few factors chosen are land pricing, energy availability, raw materials availability, utilities, road transportation, water transportation, and also local community. So as you can see, for land pricing, the most affordable is the highest ranked. The energy availability and also raw materials availability as well as utilities, we rank it the highest with the most number of sources. For road transportation and water transportation is the hub that is the nearest from the site location. For local community, we take it as the most ranked. The highest rank is when the location is suitable for heavy industry and actually the local residential area is quite far from the site location. So based on the ranking of the factors, we can see that Gebeng has the highest number of score. The overall score, Gebeng has the highest. Because of that, we have chosen Gebeng as our location for our industrial plant. And as you can see, this is based on Google Maps. This will be the location of the plant.
My name is Elaine, and today in this section I'm going to talk about the process screening on the conversion of plastic waste to food. So the process of converting the plastic waste to food is through thermal decomposition. So there are two ways. First is pyrolysis and the next is gasification. So in terms of process, the pyrolysis occurs in the excess of oxygen, while the gasification requires oxygen. And in terms of temperature, the pyrolysis occurs around 350 to 600 degrees Celsius, while the gasification occurs around 800 to 1200 degrees Celsius. And for our project, our main product is the liquid gasoline, diesel, heavy oil, and syngas. So therefore, the pyrolysis process is being chosen because of the main product, which are the liquid and gaseous fuel, compared to gasification, in which the main product is only the gaseous fuel. And other than that, the pyrolysis produce higher quality syngas compared to gasification. So this is our block diagram process flow for the pyrolysis. So over here we have the pre-treatment, in which the polypropylene is being dried and crushed into smaller pieces. Then here we have the pyrolysis reactor. This pyrolysis reactor will thermal decompose the polypropylene into the hydrocarbon compounds, which are in gaseous form. And this condenser here will condense the hydrocarbon gases into liquid, which is known as bio-oil. And here we have our hydrotreating reactor, which converts the unsaturated hydrocarbon to saturated hydrocarbon through the reaction of hydrogen in the hydrogen separation section here. And finally, the bio-oil is being split into its components, which is gasoline, diesel, heavy oil, and syngas, through the distillation process. So this is the reactor selection for the pyrolysis reactor. We have three types of reactor, which is batch, fixed bed, and fluidized bed reactor. As you can see here, the plastic plays a role in the oil and gas use. So therefore, the reactor selection is based on the advantages and the disadvantages of the reactor. So these are the advantages and the disadvantages of the reactor. So based on several literatures, the most common type of reactor that is being used in the pyrolysis process is the fluidized bed reactors here. This is because the fluidized bed reactor provides good mixing between the reactor and the catalyst, and also provides good heat and mass transfer. This is because the catalyst is being bubbled in the fluidized bed reactor. So our next part of the process screening is the effect of temperature and catalyst. So in terms of temperature, the temperature of 450 degrees Celsius will provide the highest yield. And in terms of catalyst, compared to kaolin here, the zeolite catalyst actually provide higher yield compared to kaolin. And this is because the zeolite catalyst contains the silica and aluminium compound, which is most suitable for the thermal cracking of the polypropylene. This is the hydrotreating reactor selection. So there are four types of reactor, which are the fixed bed, evaluated, moving bed, and slurry. So in the hydrotreating reactor, the fixed bed reactor is commonly used because it provides the highest reaction efficiency compared to the other three reactors. And furthermore, for example, if you use the moving bed reactor, it requires special control valve to maintain the close control of the solids. And furthermore, if you use the slurry, it is highly dependent on the quality and the performance of the catalyst. So our last process screening is the separation unit selection. We are using the fractional distillation column because we only want to separate the bio-oil into its components. And furthermore, the vacuum distillation is only used when the components are heat and air sensitive. And the catalytic distillation is mostly used for the gasoline purification, rubber extraction, and to form plastics. This is the process unit summary of the process screening. So we have our pyrolysis reactor, which is the fluidized bed reactor, which uses zeolite as catalyst and the temperature of 450 degrees Celsius. We have our hydrotreating reactor, which is the packed bed reactor. And finally, the distillation column, which we are using the fractional distillation column.
My name is Wen Jing. Now, let me explain to you the manual mass balance. As mentioned in the process screening, the polypropylene need to undergo several processes in order to obtain our final products. First, the polypropylene need to undergo pyrolysis reaction to obtain a pyrolysis gas which contains propene, 1-octane, and other components. At the same time, there is a side reaction occur that convert the 1-octane and hydrogen gas into N-octane. Then, the pyrolysis gas will enter the cyclone to separate the carbon, which is the solid char, and then enter the condenser to separate the condensable gas and non-condensable gas. The non-condensable gas will undergo steam reforming process to convert methane to carbon monoxide and hydrogen gas by assuming 70% of efficiency. Then, the stream 8 will enter the water gas shift reactor to convert carbon monoxide to carbon dioxide and hydrogen gas by assuming 19% of efficiency. Then, the stream 10 will enter the pressure swing absorption reactor to separate the carbon dioxide based on 69% of efficiency. Now, the stream 12 can enter the hydrotreating reactor together with stream 6, which is the condensable gas. This process is important because we need more paraffin and olefin in the final products. So, we will convert the 1-octane and hydrogen gas into N-octane. The efficiency is assumed 59%. Now, the stream 13 will enter the first distillation column to produce stream 14 and stream 15. Since stream 14 will enter the second distillation column to produce gasoline, its composition will mostly based on this composition. So, the 1-octane will times with 0.074, N-octane will times with 0.402, whereas the cyclooctane will times with 0.524. Then, the stream 14 enter the second distillation column and the component which I mentioned just now will exit at stream 16 as gasoline, whereas the other components will exit at stream 17 as syngas. Now, for stream 15, it enters the third distillation column to produce stream 18 and 19. Since stream 19 will enter the last distillation column to produce diesel and heavy oil, this stream will basically follow the diesel composition. To obtain the diesel composition, we will times the cyclooctane with 0.679 to get this value, so that the cyclooctane in stream 19 will be 15.3%, which is same with the diesel composition. Then, the stream 19 enter the last distillation column, and to get the diesel, we will times the 1-octacotane with 0.011, which is same with the diesel composition to get our diesel.
So now, let us move on to economic evaluation. Economic evaluation is needed to be performed in order to investigate the capability of the project in gaining profit. There are several things that are needed to be calculated, such as total revenue and also total raw materials cost. So here are the two references for waste polypropylene cost. So maximum price is selected as raw material cost. So these are the selling price of each products. So the selling price is determined based on the market analysis of forecast price that I have explained in the literature review part, which is lower than the market price because we need to compete with stable competitors in the market. So here are the total raw material cost, the mass flow we got from the questions, and the price we refer to the Malaysia trade key, and here we got the total price. Next is the total revenue. So here we got the value from the simulation of HYSYS in terms of kg per hour. Then we convert into unit conversion for each product. Then we got the production per year. Then we times with the selling price for each product. So we got the total price. So here the total revenue, here we got after the summation of 4 products of total price. So Here, in order to calculate the profit, the total revenue need to minus with total raw material cost. So here is the value of the total profit, which is in positive value. Thus, this project is economically feasible to be done.
This is our process flow diagram for the pyrolysis process. So over here we have the pre-treatment whereby the polypropylene is being dried and crushed into smaller pieces. And this is, as mentioned earlier, this is our pyrolysis reactor, which converts the polypropylene into the hydrocarbon gases. So this cyclone actually separates the hydrocarbon from the solid char, in which the char will be used in a combustor to provide energy for the pyrolysis reactor. And over here we have the condenser, which condenses the hydrocarbon gases into condensable gases and non-condensable gases. For the non-condensable gases, it will be go through these processes. Okay, so for the first process is the steam reforming, in which the methane here will react with the water here to produce carbon monoxide and hydrogen. And over here is the water gas shift reaction, in which the carbon monoxide will react with water to produce the carbon dioxide. And this process here is known as the pressure swing adsorption, in which it will separate the hydrogen from the carbon dioxide. So stream 11 here have the hydrogen. So this hydrogen will react with the condensable gases in the hydrotreater here. And this hydrotreater here will produce the product, which is called stable oil. So over here we have 4 distillation units. So the first distillation unit is to produce the gasoline product and the syngas. And the third and fourth distillation column is to produce the diesel and also the heavy oil fuel component.
Now, I would further explain on the heat integration of this project. Heat integration is carried out to reduce the cost of energy by reusing the available heat energy from the process through heat exchangers. In this project, the delta T mean was set at 10 degrees Celsius and the pinch temperature was at 1024 degrees Celsius. And based on our HYSYS, we were able to determine 4 streams, which are 2 hot streams and 2 cold streams. And based on the information collected, we were able to carry out the heat cascade diagram. And based on the heat cascade diagram, we can notice that the QH mean equals to 0 kilowatts, while the QC mean equals to 41,820 kilowatts. After collecting this information, we were able to draw out the heat exchanger network. And based on the diagram, you can notice that we have 3 heat exchangers and only 1 utility, which is a cooler, at a size of 41,820 kilowatts. And based on the diagram, you can also notice that we do not have any heat exchanger above pinch. Our whole process occurs below pinch. Now, in this project, we were able to reduce the number of utilities from 4 to 1 with the aid of heat exchangers. The cost of setup of these heat exchangers may be high, as their capital costs could increase, but on the long run, we will be able to save a lot of energy in the process plant. Thus, it will reduce the operating costs in coming time. And the overall heat recovered based on the heat integration is 33.27%. As you can see in the table, previously we had heaters where we would require 10,419 kilowatts and coolers 52,249 kilowatts. And after heat integration, we were able to reduce this and save about 20,848 kilowatts. Thus, as a conclusion, based on the heat integration done, we were able to save 33.27% of heat.
So I'll be explaining about the process control and PNID in this industrial plant. So this is the PNID before integrating the heat integration. So the control strategies used in this system is feedback control system and also ratio control system. There's only one ratio control system, which I'll be explaining later on. So I'll be explaining few examples of few units and the types of control variables used and also the manipulated variables of that unit. So in this case, the first example will be the hydroprocessing reactor, which has pressure, temperature, and level as its controlled variables. And in terms of manipulated variable for the pressure, The liquid flow rate is the manipulated variable leaving the reactor as shown here. The temperature will be the energy input to the heater here, and also for the level, the liquid flow rate leaving the reactor. And these are the desired values for pressure and temperature. The next example will be one of the distillation column, and the control variables are temperature and also the level. For temperature, the manipulated variable is the fluid entering the distillation column. For level, on the other hand, is the fluid leaving the distillation column at the bottom and also the distillate stream. And this is the desired value for the temperature. The next example is another reactor, which is gas shift reactor. For this, there are three control variables, which are pressure, liquid, and also flow. For pressure, the manipulated variable is gas flow rate leaving reactor, which is here. For the liquid level is the liquid flow rate leaving the reactor here, and also for the flow, the fluid flow rate before the input reactor is the manipulated variable, and this is the desired value for pressure. For ratio control, as mentioned earlier, there's only one ratio controller which is used for this mixture, and the function is to regulate proper flow between these two streams. These are few examples with controls, the control variables for these units, and also the desired value for those control variables. And this is the PID after heat integration. As you can see, there are heat exchangers here, here, and also here.
Hi, I'm Hui Jing. For the hazard analysis, our first node is the pyrolysis reactor. No flow, less flow, and more flow might occur in this node. The most serious matter is the contaminant due to the leakage in the reactor. The pyrolysis gas might react with the oxygen and cause explosion. For this scenario, our current production is the flow controller and the scheduled maintenance and also the standard SOP. For future recommendation, we will install the nitrogen ramp, which can help to emergency shut down the plant and control the pressure vacuum condition in the reactor. The less pressure and high pressure will also occur in this node due to the leakage and blockage of the pipeline. For future recommendation, we will install high pressure alarm, low pressure alarm, and pressure controller. Our next node is the pyrolysis reactor to the cyclone. In this node, no flow might occur due to the failure of valve to open and the blockage of pipeline. This will disturb the production, and for the worst case, the pyrolysis gas might re-enter the reactor and cause explosion. Our current protection is the flow controller, schedule, maintenance, and SOP. For future recommendation, we will try to install nitrogen ramp and flashback arrestor. Flashback arrestor can help to stop the flame from burning back to the reactor. Besides, less flow will also occur in this node due to the valve is partially open and the leakage in pipeline. The possible consequence is the pyrolysis gas will release to the atmosphere and cause explosion from the leakage, and the pipeline blockage will occur due to the accumulation of the solid charge that present in the pyrolysis gas. To solve this problem, we can have a pipeline strainer, automatic valve, and the low flow alarm. The pipeline strainer can help to remove the solid charge from the flowing gas. Besides, more flow and the reverse flow will also occur in this node due to the valve malfunction. These both of them will cause the pyrolysis gas to enter the reactor or the release to the surrounding and cause explosion. For that, we will try to install the check valve, flashback reactor, and also ensure administrative inspection only. Our last node is the hydrotreating reactor. No flow, less flow, more flow, and also reverse flow will also occur in this node due to the valve malfunction, leakage, and the blockage of valve. This will disturb the production and affects the quality of the final products. So, the current production that we have now is the flow controller at the feed stream of the mixer and scheduled maintenance and standard SOP. For future recommendation, we will try to install low flow alarm, high flow alarm, high pressure alarm, check valve, and also ensure administrative inspection only. Lastly, low temperature and high temperature will also occur in this node due to the leakage in reactor, low and high inlet stream temperature. This will cause the process upset and the incomplete reaction. For future recommendation, we will try to install low and high temperature alarm.
So based on our objective of project, our goal is to convert the plastic waste into fuel. So we do that by doing the market analysis so that we can know that which fuel is high in demand. And next is we do the process screening to determine which process is suitable to produce our product. And next is the plant location to determine which location is suitable and safe. Next is the hazard analysis to determine whether the process is safe and also safe for the workers. And next is the process flow sheeting as a reference for us and also to check with the mass balance. And finally, the process instrumentation and PNID to determine the controllers for each equipment. So that's all from us. Thank you.